You have to detect all of these problems. You have another black and white choice. Can you do this without stable sample QC? Yes or no? If you have to do stable sample QC to detect an error, then how often do you need to do it? I'm going to review this. We saw it last 2 weeks ago. Which of these products can you ship before verifying it meets customer specifications? Was it ever truly, really proven that we should report patient results before checking the QC? Here's what happened when we checked the ability of QC. We simulated a clinically significant error. This group, in 2012 to 2014, only 17% of them could detect that error in the first run versus 39%, 60%. The principle of testing QC samples is that what happens to your patients happens to your QC sample as well. What if the method really failed back here? At the least, the ability of the QC procedures to detect medically allowable error should be evaluated. What is the potential risk if the method fails? We're going to go back into another simulator. We're going to look what happens if you do the mathematically optimized QC process versus what happens with typical lab QC. The lab controls these four numbers: QC chart mean, QC chart SD, QC rule, QC frequency. With those four numbers, by adjusting those four numbers, you can maintain whatever acceptable risk level the medical director has set, or you can shut down the method and improve it. Take it back to him or her and say, what do you want to do now? These three numbers, chart mean, chart SD, and the QC rule, drive the two outcomes. Are you able to detect unacceptable risk immediately, and how many runs would it take to detect that unacceptable change? So we simulate a shift after the blue line, risk is unacceptable. You can see here it's probably going to take 2 runs. One number drives the acceptability of potential risk, and that is the QC frequency. We're going live again. So come over here to QC design. The current risk is reflected in the margin for error. Select a QC process to match the margin for error. So what we're going to do is we're going to look at the margin for error. We're going to come over here and say, for this margin for error, for this range, which means from this percent to this percent, or from 1 in 52 million to 1 in 3 million, and then you get right down here to say 1 in 44. If I get down to 1 in 44, I've decided I'm going to stop. If I'm above that level, then you need a full QC strategy. The frequency of the QC samples, the type, the number, the statistical limits, they don't need to be rules, they're statistical limits, the frequency of looking at your charts for shifts and trends, and the action to take. There's much more to QC than just a QC rule. So you can adjust the QC rule, you can adjust the sample frequency, you can adjust the QC chart review, you can adjust the supervisor's review, you can recommend specific action, and you can see how this could all be easily just driven straight from the numbers. There is the link here. This neat place will let us convert any sigma value, any z value, to a percent or vice versa. So let's come back over here. This is our risk evaluation chart. This is the change chart. This is the tab we're going to use to decide how many runs to reject. So now I'm going to simulate a clinically significant error. I'm going to simulate a shift so that 5% are failing. This has a margin for error of 0.5. That is an extremely small margin for error. You're not going to detect a shift of 0.5 SD. That's a sigma of 2.5, by the way. This is a sigma of 2.5. This QC chart right here, this is a test with a sigma value of 2.5 using a 1-2S rule as a reject, and that's what it looks like. This is a shift of half an SD. Now, if I can bring this mean back to 100, I've changed my mean down to 100, now my margin for error is 3, now my sigma value is 5. Now let me get those drawings off here. Now I don't need the 1-2S rule as a reject. Now I can go in here with a margin for error of 3. I come over here and say I can use a 2.5S rule. So I come over here, I say I'll take a 2.5S rule. Now that I can see that there are 0 false positives beforehand, the odds are still pretty good that I'm going to detect that change in the first run. So I can say yes, probably, not likely, or no. I'm going to say probably, and I'm going to note this as the estimated runs to reject as 1. The trick is, what does the lab do? Most people, and you can look in the mirror if you like, at least double the standard deviation on the QC chart. A lot of people tend to use the same QC rule for all. When you double the number on the QC chart, what happens is you've doubled that, so you've doubled the QC rule. What the lab did with their QC, they doubled the SD on the QC chart, and they're never going to see a QC flag, never. So will this detect change? No. Runs to reject, good grief, it could be 20. If I come back here and I'm going to put the assigned SD on the QC chart, I put the 2.0 on. Now this method, so I've got a mean of 100, an SD of 2. This one is using a 1.3S and this one is using a 1.2S. Look at the difference in the error detection after the QC flag, after the reject, after this simulated shift. The QC rule you use and how you assign the values on the QC chart determine exactly the number of runs to reject. The runs to reject times the number of people, or times the number of people in a run, are the number of people at risk. You can see here there's more to a QC process, and that's spelled out very clearly in both IQCP and EP23. There are 5 parts to a QC process. You get them from here. You can look at sigma values, you can look at margin for error. You can't really use the percent risk, they get down to such small values, but it is fascinating to look at what you're really doing here for 1 in how many patients. So you could tell your patients there's a 1 in 44 chance something might happen. Here's what happened. We looked at 605 QC samples. These ones on the right are from 2000 to 2014. This is both the same set, actually. These are both the same QC samples from the same methods. On the right is actually how the labs did quality control. On the left is what happens if you mathematically optimize it. So if you pick and choose the proper rule for each QC chart according to the margin for error, and you put the real values on a QC chart, you can more than double the number of methods that are able to detect a clinically significant failure in the first run. So all the studies that have been done on the numbers of lab errors, whatever the numbers are, you can argue them, but if you're using a method that has hazards that are only detected by statistical QC, then you should be governing your statistical QC to detect clinically unacceptable risk. Here's why this happens. Everybody does QC differently. I've done this survey and it's still up. Some of you have taken it. Everybody takes their mean, their SD, and their rules for the QC charts from a different place. That's not how it's written. That's not the theory, but it certainly is the practice. The optimum QC process is a calculation. It's not an opinion. This is what people do. This is the study that we were looking at. These are the 33 labs. This is the measured CV on the bottom on the y-axis versus the assigned on the top. This is a measured CV of 4 with an assigned CV of 20. Almost unanimously, they have assigned the SD higher than it really is. When you assign the SD higher than it really is, that means the QC rule is going to take longer to detect a clinically significant error. It's not changed in 15 years. This is from the year 2000. This is what they did then, and it's broken down by different analytes. This is around the world, around departments, around every lab that I have ever been into. People have missed the very fundamental instruction to put the mean and SD that you measured on the QC charts. When computers came in the 80s, they created the ability for people to do things wrong so easily, and we just picked it up and went with it. If you use a mathematically optimized process to select QC rules, as the analytical process quality becomes better, you lower the potential risk and you lower the runs to reject. But that's not at all what we see in real practice. This is another example of it. This is with statistical QC on the left. So this is what the labs are doing on the left versus the old software that was around in the year 2000, and you can't even buy it anymore. No runs to reject above 11 versus look what's going over here with statistical QC with the number that will never ever detect a clinically significant failure.
Individualized